Hi roboticist! Finally today we are gonna code a pick and place application in C++ using MoveIt framework in RV's environment. I'm gonna to step you through all the process to have the best understanding that you might looking for, telling you how the code is structured, how each objects are made, and what each function does in order to accomplish a proper pick and place application. Then we will test our application trying different way to pick and of course different way of placing the object that we are going to create in our scene. So if you are really interested in this type of video, make sure to subscribe to the channel, hit the notification bell in order to do not miss the next topic. And furthermore, if you like the way I teach, have a look on my ROS course for beginners, where you will be transformed from a total beginner in robotics programming to a really good intermediate level of ROS. Competence that nowadays are very useful to have in industrial field. The course is structured as I would have liked to learn ROS, because I really understand the conceptual difficulties you have when you start programming robotics application from scratch, especially with robot operating system. And don't forget that the main advantage to this is that you can also download all the lessons for learning whatever you want. So it will be absolutely worth it to have a look on it, and you can now benefit a 50% discount with the code WELCOME50. And don't worry about that, I'm going to put the link in the description down below. So now let's get started. Open a new terminal and navigate into the Code test package and open Visual Studio Code. And in the source folder you can see all the C++ code that we have created in the previous video. I'm gonna put the link in the description down below if you wanna check out. Then create another file and let's call it pick and place cobot.cpp. Okay, here we are. We can start from scratch. So we need to tackle somehow this problem of pick and place. And what I'm gonna do now is to give you a structure between the package that you need to include in this file, then the main, and then the function that you will need to operate this pick and place application. Here we are. Some package we have seen already in the previous video. I don't want to go too much in the detail. What is useful to have here is a constant that let's call it tau. So this is gonna be one round, let's say, at radians. So tau is gonna be one rotation in radians. Okay, so now what we can do is to create our main section. So nothing new for the moment. As always, we need to initialize the node and give it a name. We can call it cobot pick and place. Then initialize a node handle object to handle better the node that we have created, and then the spinner function. So let's sleep the code for 1 second. You will see later why. Then we need to create a planning interface object belonging to the planning interface planning scene interface class, and let's initialize this object by planning scene interface, and then initialize an object move group interface, and we need to call the name of the robot that we have set up in our MoveIt configuration wizard. Then we're gonna pick the object, so we are going to code a pick function where we are going to pass the move group interface object that we have just initialized in this main function. Then again wait a little bit. And finally we need to call the place function, where this pick function of course is supposed to pick the object in the way that we are gonna code in a while, and then we need to place somewhere in a way that we are going to code afterwards. And then let's shut down this node by using the wait for shutdown function return 0. Okay, this is the main function. As you can see, it's very simple. You're gonna have the add collision object where we are gonna create our environment with the table and the object that has to be taken, then the pick function and the place function. So for now we need to code at least 3 functions. So let's start by coding the add collision object function, where, as I said, we need to pass to this function this planning scene interface object belonging to the planning scene interface class. Okay, before to code this function, let's understand first the structure of this code. So there will be, as I said, the add collision object function. Then there will be a pick function. So it's gonna be place. And then we need to pass as an input an object instantiated in the main function that is belonging to the class moveGroupInterface. And so the object that you're gonna pass in this function, we can call it moveGroup. So afterwards there will be the place function, where, as before, we need to pass the same type of object, but this time in this place function we can call it group in order to differentiate that. Okay, these are the main structure. There's the main, the add collision where we create our scene, then the pick and place object. Okay, what we can add further, you can imagine that if you pick an object at a certain point, you can imagine that you need to close the grippers of your robot, right? So you need to first open the gripper, take the object and then close the gripper. So we are gonna code two other additional functions that are responsible of open the gripper and close the gripper. So I think that up to now is gonna be intuitive. So the input that we need to pass in open gripper function, it will be of type trajectory message join trajectory, and we're gonna call it posture, and it will be the same type as the close gripper. But basically these two functions will be very similar, as you're gonna see in a moment, with just the difference that open gripper set the gripper right at a certain value, and the close gripper with another one. So the pick function will call the open gripper and the close gripper. Then the place will call the open gripper, because after that the object has been put in the target position, then of course the gripper has to open. Okay? So very easy, I think, till now. Okay, so first of all, let's start to populate these five function, and let's start from the add collision object, which I think it will be the easier one, because the easiest one, because we have already done it before. So we have created a collision object, let's say, and we have used the primitive shape in the previous video, so there should not be any surprises. So I'm gonna go pretty quickly, and I'm gonna put the link in the description down below regarding the video where we have already talked to that more deeply, let's say. So we need to add the first table, and we can call it table 1. Then we need to tell that this table is gonna be positioned with a reference frame of the base link, where we need to pass the header and the frame ID of our collision object. Before to create an object, I think that is gonna be better if we visualize first where we are gonna put the object and how the pick and place will behave. So here there's the base link, which in our environment is going to be 0, 0, 0. Then here in position x1 and y0, there will be the table 1. So this will be the x direction, and this the y direction, and the top will be the z direction. Okay, something that you have already seen. Here there will be the table 1, as I already told you, and here the table 2. And there will be an object that will be posed on the table 1, and the goal will be to put the object on the table 2 in the same configuration, let's say. So after this introduction, we can continue. So we need to define our primitive dimension and the position in orientation of the table 1, where is gonna be a box, and then we need to put the dimension and the position orientation of the box, or better, let's call it table 1. So the box will be 020404 meter, and then this will be posed in position x1, y, z, and y0 and z 0.2, where the center of the table will be posed at the z position 0.2. Okay, then we need to add the object, calling the method add, and then we need to do the same for the table 2. The dimensions are pretty the same, with the exception that we need, of course, to update the position of this vector collision object. The position of this table 2 will be now in x0, y1 and z 0.2, so same height, and the real part of the orientation will be 1. And finally we need to define the primitive dimension of the position of the object that we want to pick. So here it will be the same, just update the position of the collision object and then the dimension, of course, will be different. Okay, that's it for our environment. We have created the table 1, the table 2, and the object that you want to pick, and we have defined also the position and orientation of each object. So after that we have created, we need to, let's say, spawn in our environment by calling the apply collision object method and passing the collision object that we have modeled in this function. Okay, before to go further, let's run this node to see where the objects are. So to do that, since that is a C++ code, we need to update our CMake list text file, where we need to create our executable file from the pick and place cobot.cpp file that we have just created. Nothing new, and then build the package. So everything was built properly. So launch the demo.launch file belonging to our Cobot MoveIt package that was, I remember, you automatically created from the MoveIt setup assistant. And then we can run our pick and place Cobot node from the Cobot test package. And here you go. You can see that we have our three objects, the table 1 and the table 2, and this will be the object that we want to pick. is in the table 1 is in x0 x1 sorry and y0, and the table 2 will be in x0 and y1. What we would like to do here is to create a code to make the end effector of our object to pick this object 2, which is gonna be a stack, let's say, and place in the table 2, and we are gonna figure it out what will be the orientation of our TCP to pick in the best efficient way. So the most important thing to bear in mind is that the orientation we are gonna select by choosing the roll, pitch, yaw angle. So the blue is the axis of rotation that determine the roll, the green will be the pitch, and the red will be the yaw. Basically what I'm gonna do, what I'm gonna code in as orientation of the TCP will be to make a roll rotation angle of a quarter of rotation and a quarter of rotation of the pitch angle, so through the green axis. Offline you can think about it, and you can have this in mind, how to pick an object. I understand if you struggle to visualize the movement that the TCP needs to have, but after some let's say practice, you are gonna understand better what is the angle that you will need to put as a new orientation setup of the TCP for the peak position. So we're gonna discuss it later, but now after this introduction, let's populate the peak function. So first of all, you will need to create a vector belonging to the class grasp, and what that you need to know is how the grasp class is structured. So when you're gonna pick an object, you are gonna select the position of the picking, but first you need also to determine the position of the approaching, and then the direction for approaching the pieces, but we are gonna see in a while. So what we're gonna do now is to modify the grasp object that we have just created. So first of all, you will need to determine the reference frame where this object is referring, and it's gonna be the base link as always. And then you need to create an orientation object, or better a quaternion object, and let's call it orientation. And this is very useful when you want to set up an orientation by choosing the angle of roll, pitch, and yaw. And as I said, now we are gonna try a peak orientation. Let's name it test 1. And so you need to set the RPI, and now here you're gonna find the angle that you need to put from the start position to the end position. So this orientation angle is the rotation in row, pitch and yaw that your link in general needs to do from the starting position to the end position. So in this case we want that the TCP makes a rotation in the role of a quarter of rotation and a quarter of rotation in the pitch angle, and this will be the peak orientation. After that the robot will be ready to pick the object. Okay, and then we need I remember you that MoveIt accept, let's say, orientation angle given in quaternions. So since that we have set up an angle in a row, pitch, yaw, we need to convert them, and to do that we use the function to MSG. Okay, so after that we have set up the orientation, then we need to set up the position in X, Y, Z, and you can imagine that this will be simpler. So what I'm going to set up is the position in X, Y and Z, that respectively is going to be 0.915 in X. Of course it cannot be 1 because the position 1 in X is exactly where the center of the object is, so we are gonna have a collision, and we don't want to do that. We just need to stop the TCP just before that the end effector reaches the object. You need to select the position in X, Y, and Z, and since that we are going to pick the object through the Y position, and the position in X will be aligned to the object, so X will be 1, then Z, it will be the same Z position of the object because we are gonna grasp at the center, and the Y will be a little bit offset of 85 millimeter. This is because we don't want the TCP to collide the object before to set it up in the right position. Okay, so consider that this will be the position where the end effector will be at. After that you will close and the object will be picked. So as I mentioned before, the picking process, before the picking process there will be a pre-grasp approach. So meaning that you want to set up a direction and position of the TCP that needs to go to approach the object. But we are going to see to visualize it better. For the moment, just trust it, and as we did for the grasp pose, we need to select the header and the frame ID, which is going to be base link. And then you need to give now a direction to approach the object, and since that we are going to approach through the positive y direction, then we need to put vector dot y equal to 1, and then you just need to create the minimum distance and the desired distance. Okay, so as you can imagine, the grasp pose and pre-grasp approach are methods belonging to the class grasp, okay, of the object that we have instantiated, that is called grasp. Okay, after that, since that we have a grasp, a pre-grasp, then we're gonna have a post-grasp retreat, and as you can imagine, you're gonna give a direction of your TCP after that the object has been picked up. And so what we're gonna do after that the object has been picked, we are going to go to the positive direction in Z, and then you need to select also the minimum distance and the desired distance. I'm sure that after that you're gonna visualize, you will understand very quickly. So another function that we need to call is the open gripper function, and afterwards we will need the close gripper function. And the open gripper function takes as an input the pre-grasp posture, because after that the TCP has in position ready to approach the object, you need to open the grippers. Then afterwards you need to create to set a support surface as a table 1, and finally you need to call the pick function to pick up the object using the grasp that you have passed in. So before to continue in the place function, we can build the code and test it right away. And in order to visualize better the behavior that the TCP has in the approach and the grasp and in the retreat. So let's run the pick and place code, the pick and place node, and you're gonna see the table and the object, and then you can see here that the robot is doing his pathway. So he's going to the position, is going to the pre-grasp position, then is going to approach in the positive y direction the object, and then is going to retreat in the positive z direction. So again, pre-grasp approach, then we are setting in as an offset of 85 millimeter in a negative y direction. Then we approach through the positive direction of y. Then there will be the close function that will close, and after the closing it will retreat the object to the positive direction of Z. So I hope that I hope that you got a better understanding of how this grasp object is structured. So now we are ready to code the place function. And basically the approach it will be the same. So we need to pass as an input the move group interface object, and then we need to create a place location object, and with the same approach that we did for the grasp object in the pick function, we need to modify, or better model, this place location object. And first of all, you need to have a frame ID of this object that is going to be a base link. And then we need to do the same. So we need to create an orientation, a quaternion object, because we are going to set up the row, pitch, and yaw. And now we are going to determine the orientation of the TCP after the place, when it's placed, take into consideration that it started from the peak position. Okay, so if you think, since that we need to put in the in a table 2 that is 90 degrees, let's say, from the table 1, then we need to make a positive quarter rotation in the z-axis, which is gonna be the yaw angle. So basically you have it here, and then you will think that the object will be put in the table 2 and is gonna make a rotation, exactly a rotation of 90 degrees. Okay, after to have determined the orientation, what you need to do is to set up the position, and this will be easier. So the x will be 0, the y will be 1, and the z will be 0.5. You can very easily visualize in RVs. So now we need to set the pre-place approach, so meaning that we need to give a direction of where this object will be placed. And if you think, in the peak we have used as approach of positive z, then we establish only a rotation of this object, and then we will need to go negative z of the same amount in order to pose the object on the table 2. And after that you need to set up the post grasp retreat, so meaning after that the object has been placed, where the TCP will need to go, in which direction, of how much. Well, this information has been stored in the function, or better the method post place retreat. And in this manner we are gonna go in the negative x direction. And then since that it is a place, you need to call also the open gripper function. So I remember you that is not sequential, okay? So because it really depends on the object that you're gonna create. The place, pose, place approach and post place approach, they are not called in the order that we are gonna put in our C++ file. Okay, so don't worry about that. And then you need to, as we did for the pickup function, to set the surface as table 2, and then you need to call the place function to place the object using the place location that we have given. If you test it out, you will realize that the program will not go further. So why that? Well, because you need to create the open gripper function and the closed gripper function. So let's do it, and this will be very easy. You just need to call the joint name method of the joint trajectory class, and then you need to put the position when it's gonna open. And if you remember, we are going to determine the position of only one gripper out of two, because we have set up the gripper left joint as a mimic one, so we need to determine only one angle. And I remember to you that if you want to go through the URDF file of this cobot, you just need to if it's gonna be 0, then the pick and play, the gripper will be opened, and on the other hand, if it's gonna be 0.0.5, it's gonna be closed. Okay, something before to test, something that I forget to put is to resize the place location. So after that we do that, we can test it out. Okay, here you can see that is picking, is grasping. Then when it's grasped, the object will change the color, and then it will go into the place position. Okay, it's gonna to approach the place position in the negative Z, and is going to open the gripper and then retreat in the positive Y direction. Okay, what I wanted to point out is that you can imagine that this is not the most efficient pathway to go to the place position. It will be better to go into straightforward, let's say, to make a 90 degrees of rotation rather than 270. But what I wanted to let you know is that every time that you create a motion planning, the algorithm will change every time. Okay, and here you go. You can see that if you run the code again, then the robot from the actual position will go to the peak position and then to the place position as well. So feel free to try different setup and check what are the different pathway that your robot will do. But in regardless the motion planning that the robot will do, it will always pick and place at the same position, and they will always have the same retreat and approach. So for example, if you kill all the nodes and you span it and you test it on another and you test it again, you will see that now the motion planning will be different. And in fact, it seems that now it's going straight forward to the peak position, and then the place is much better, you know. So I didn't do nothing. I just let MoveIt do his work, and basically this is a really straightforward pick and place application of an object from table 1 to table 2. And then you can see all the movement, the approach, the grasp, the retreat, then the place, the approach again, the release of the object by calling the open gripper, and then finally the retreat. And of course, to have a very good pick and place application, you need to study upfront what will be the orientation of your TCP, what will be the approach, the retreat of the peak, and in the place. Okay, that's all for this test. Before to leave you playing and get some fun, I just wanted to show you how the motion planning change if we change the angle of the orientation of our TCP. And instead of picking the object through, let's say, the positive y direction, what we're gonna do is to pick from the negative y direction, and you will see in a while how this motion planning will change. So first of all, let's comment everything that is belonging to the pre-grasp approach, the grasp pose, and the post-grasp retreat, and we need to change it accordingly. So for example, in this example, I just changed the orientation of the roll angle, the opposite one, and basically the position in y, and then of course the direction of the vector y will be opposite. Let's do the same modification for the test 2, and let's see how we can place this object. We keep the same rotation angle, and it will be anti-clockwise. You will figure it out after that you see the TCP moving from the peak to the place position, and then the retreat will be in the negative x, because you can imagine that the TCP has a different orientation, so it needs to retreat in another direction. but you are going to visualize it right away. So build the package again and run the code. Now he's approaching from the opposite side. Okay, he's speaking, the object is turning purple, and then he's going to the place position. Okay, this is acting, let's say, weird. It's not necessary that the cobot makes this turn. It will be just straight. But I'm sure that if we run it again, it will be much straightforward. Okay, and then, but the point here is that now you can see that the motion planning is different, and then we needed to update the retreat from the negative x, because we have changed the position of the TCP in the picking position. Okay, so let's run it again, and I just click plan and execute, so it will go to the start position from the actual position that will be after the TCP to be retrieved after the place, and then we can run again the code. Okay, we are ready, so let's make a reset, and then run the pick and place node again and see what's happened if the motion planning will be different, the trajectory will be different. And here we go, it's pretty much straightforward. And then the place, let's see if it's making the weird pathway. No, it's straightforward now. Okay, so because while you are operating, MoveIt will find a better pathway that is, let's say, it's optimized, and I think that this will be a pathway that I would say pretty much straightforward. Okay, that's it for this video. I hope that you like it. Feel free to modify the pick and place position, retreat, grasp, whatever you have seen now. I hope that you enjoyed this video. If you like this video and if you like this kind of content, comment in this video to give me a feedback if you like this video, or if you want me to treat other topics like that. So please consider to subscribe to the channel in order to have similar topics like that. My approach will be more industrial one rather than a hobbyist one, so I'll try to teach how to program robotics for industrial application, like a pick and place is very often used. And in order to support the channel, also gives a thumbs up, subscribe to the channel, and you can have a check on my course in beginner in ROS. I'm gonna provide the link in the description down below. Okay, again, thanks for your attention. To keep learning robotics with ROS.